Hello everyone, my name is Kritika from Code Hiroko, and in our today's video, we will be going over
Introduction to the Chatbot course.
At Code Hiroko, our mission is to make world-class computer science and engineering education accessible to millions of students, especially in developing countries like India. We will first talk about the NLP pipeline, and we will look into the steps involved in building an NLP-based chatbot. Then, we will learn about the steps involved in pre-processing of data, such as tokenization, lemmatization, stop word removal. Once we have understood how to curate a list of words, we will explore the common encoding techniques used to convert this text into numerical vectors. Alright, now let's go over the steps involved in building an NLP-based chatbot. First, we need to have a clear picture as to what domain the chatbot will be handling, what is its scope, and the available data set the chatbot can be trained on. So let's say we are building a banking chatbot. Alright, so that time we need to have a clear picture on what is its scope. So what kind of information retrieval will it be handling? And what kind of transactional questions can it handle? And we need to have a default answer in place for certain action items as well. Our next step would be to collect the data set using which we can train the chatbot. When I say data set, it could mean anything, maybe like historical chats or other useful text documents, which would come in handy for training the chatbot. So once we've collected the data sets, we can now start building the chatbot using all these steps. The chatbot model usually consists of a neural network, but we cannot directly feed it a large block of text. As for the neural network to work or perform any activity, it needs the input as a vector, a numerical vector. So first we need to perform pre-processing step, and then in the feature engineering step, we need to perform encoding techniques so that the input becomes suitable for the model to carry out its process. Now let's dig deep into each of these terms and process. How does text pre-processing work? To understand this concept, let us take an example of this sentence. Jenna went back to the university. In our first step, we will convert this entire sentence to lowercase. We will also filter out all the punctuations. Once we have this sentence, then we implement tokenization step. In tokenization step, the words are broken down into tokens. Once that is carried out, we can implement removal of stop words. So basically what happens in this step is all the words which are not exclusively adding any value to the sentence gets flagged and we can filter out those words. So you can see that back to is not adding any extra meaning to the sentence. So we can remove it and still make sense of the sentence, right? So now we have the words Jenna went university. Then we carry out a process called as stemming or lemmatization. Here the word gets broken down into its root form. So in stemming, basically what happens is the prefix or suffix of the word gets removed. In lemmatization, using part of the speech concept, we bring it down to its root word. So went gets broken down into go. Right. Now let's explore each of these concepts in more detail. Tokenization. Tokenization is a critical step in the overall NLP pipeline. We cannot simply jump into the model building without cleaning the text first. What is tokenization? As we've already covered, What happens in tokenization is a sentence gets broken down into smaller components called tokens. What are the common methods used to perform tokenization? We can always perform tokenization using simple Python functions like split, or we can use regex expressions to split the sentence into smaller components, or we can use really cool libraries such as NLTK or Spacey. All these are very useful libraries if you want to perform any task related to natural language processing. Or we could use the Keras framework, which is very useful when we want to perform any sort of data processing on an unstructured data. Alright, now let us explore what are the common issues that are faced when we perform tokenization. One issue might be apostrophe. So if the sentence has I am with an apostrophe, right? Am, then should the algorithm split it into I as one word and am as another word? Or should it consider it as a single word, right? And what if we have words with a period like PhD or even words such as BTech? Should it split it into Bachelor of Technology? And words which have a hyphen in them. So should the algorithm make sure that each word is considered separately, or should it club it into one single word? And when we move into other languages, right, there are a whole new set of issues that come into picture. Like when we are dealing with, let's say, Japanese or Chinese, the words don't have spaces in them, and multiple times characters overlap. So that time performing tokenization becomes a challenge. Stemming and lemmatization. To understand this concept, let me paint a scenario in your head. When we are running a search, we want to find the relevant results not only for the exact expression we have typed, but also other possible forms of the word we've used. Like if we're searching for backs as one of the search, that time we would also want to find relevant search articles to the word bag, right? This is possible by these methods, stemming and lemmatization. The aim of both the methods is the same. Basically, they want to reduce the words into their base or root form. Although the goal of these two processes might be the same, these two processes are not exactly the same. Let us go over the differences between stemming and lemmatization. In stemming, the algorithms work by cutting off the end or the beginning of the word, taking into account a list of common prefixes and suffixes that can be found in the inflected word. This indiscriminate cutting can be successful in some occasions, but not always. And that is why we see that sometimes words get reduced to words which don't make sense, like how in our earlier example, university was reduced to a word which doesn't make sense just because ITY was a common suffix and hence it was removed. On the other hand, lemmatization takes into consideration the morphological analysis of the word and then it breaks it down into its root form. How do they work? Well, for implementation of stemming, a very common algorithm which is used is Porter stemming algorithm. So this has a list of basic English rules like all the ing from the words must be removed provided there's a vowel before that ing. Okay, so from singing ing doesn't get removed, but from let's say walking the ing gets removed. But this is also problematic at times because from nothing, we do not want ing to get removed, but as one of the limitations, that does happen. The key to implement Lemmatization is linguistics. So we need to analyze the word, how it fits into the sentence, and based on that, the algorithm decides its root form. So the takeaway from this slide is developing a stemma is far more simpler than implementing lemmatization. In the latter, deep linguistic knowledge is required to create a dictionary that allows the algorithm to look for the proper form of the word. But yes, lemmatization definitely gives more accurate results in comparison to stemming. What are stop words? Stop words are commonly used words such as the, and, in, and they do not contribute to the deeper meaning of the phrase. So we can always filter out such words. But the real question is, do we always have to filter out stop words? Not necessarily. Like when we are doing sentiment analysis, that time sometimes we will require words like at all. So the movie was not good at all will give us a more negative impact. So that time it's better to have some certain stop words. So basically, if we want to put it in a nutshell, stop words are words which more or less add to the contribute to the noise of the sentence. We can filter it out, but there's no universal list which says so and so words are always stop words. So we need to do a research and then decide what are the stop words that can be removed from the document and will not negatively impact our model. In vocabulary building step, we prepare a data set after the removal of the stop words. Alright, now that we have a holistic view of what happens in the data pre-processing steps, let us now dive deep into the next step involved in the NLP pipeline, which is data transformation. Why do we need to implement data transformation? Sadly, all our machine learning and deep learning algorithms work on numbers and not on text. Hence, we need to convert the text into some mathematical data, after which we can feed it into our algorithms. Hence, we need to implement this step. There are a number of methods to convert text into numerical vectors. Now, let us look into a few common text encoding techniques. Bag of words. This is a very popular method. It is called bag of words because any information about the order or structure of the words in the document is discarded. The model is more concerned about whether the known word is present or not in the document rather than where exactly in the document the word is present. This technique returns a vector which tells us whether the word in each sentence is a frequent word or not. Now let's look into another very common text encoding technique, TFIDF, which stands for Term Frequency Inverse Document Frequency. Basically, this technique helps us to understand how relevant a word is to a document in a collection of documents. How to compute the TF-IDF score for a word? Basically, we need to multiply two different matrices. First one is our term frequency matrix. One way to compute this is our normal regular raw counting of the number of times a word occurs in a particular document. Next is the inverse document frequency. This brings to light how common or rare a word is in the entire document. The closer its value to 0, the more common the word is. Multiplying these two numbers, the term frequency score and the inverse document frequency score will give us the TF-IDF score of the word in a document. Higher the score, more relevant the word is. Alright, now that we have a high-level overview of the common text encoding techniques, let us explore each one of them in detail. Let us understand the concept of bag of words model using an example. Let's assume that we've collected a collection of 4 documents, which are as follows. So this is the journey of Joe. Joe waited for the train. The train was late. He decided to take the bus. The bus station was close to the train station. He walked to the bus station and caught the bus. Our first step before we implement bag of words model would be to pre-process the data. So what we have to do is first convert this list of documents into sentences. And then sentences need to be converted into tokens. Tokens need to be converted into lemmas, and we need to filter out all the stop words. And once we have implemented all these steps, we have a list of pre-processed data, which looks like this. So you can see all the punctuations are removed and all the words are reduced to their lowercase form, and yeah, even common words which don't add meaning are also removed. Once we have implemented that, we can move on to the next step. Next, we need to iterate over each of the sentence and filter out the most frequent words. So in our case, bus, train, and station are the most frequent words in the list of documents. As a final step, we need to create a matrix. This matrix comprises of zeros and ones. So if that frequent word is present in the sentence, the index is set to 1, or else it's set to 0.
Okay, now that we have understood how Bag of Words is implemented, let's have an experience of understanding it using Python programming language. Bag of Words model can be implemented on Python using a number of libraries and in a number of different ways. In this particular example, we are using the NLTK library to understand the concept of bag of words. Our first and foremost step would be to import the libraries. Once we have that in place, we will have to insert the text that we would want to preprocess in this manner. Our next step would be to normalize the data. We will have to split the document into sentences, and we will have to clean the data. That is, convert text into lowercase, remove all the non-word characters, remove all the punctuation. So that's what this particular cell is doing. Once we have normalized the data, we will have to break them down into words. So after we have completed breaking down the documents into sentences, our next step is to break them down into words, also called as tokens. So you can see that our document, Joe waited for the train, the example that we earlier explained, right? That same text is now broken down into tokens. All right, now that we've successfully converted the text into tokens, our next step would be to implement lemmatization. This function, lemmatize, by default assumes that the part of speech is noun. So we need to write a function which will tell us what is the part of the speech. And based on that, if we pass that as an argument, it will reduce it to the right root form. So, happily is an adjective, so it needs to get reduced to happy. And running is a verb, so we need to reduce it to run. All right. So let's just implement this cell, execute this cell. You can see that here Joe waited is reduced to its root form wait. And yeah, was is reduced to be. Similarly, all the words are reduced to their root form. Our next step would be to filter out words like the, be, to. So all these stop words can be filtered out using this function. So you can see now that the text is cleaned and words like the, to are filtered out. Now that we have successfully completed pre-processing of the text, we can move on to the next step in the NLP pipeline, which is word transformation. So here our first step would be to make a
a list of the counts of the most frequent words occurring in our document. So you can see here that words such as train, bus, and station are the most commonly occurring words. So let's next form a matrix which will tell us the details of which sentences has these frequent words present in them. So if we implement this and print out the array, we can see that this is the same array that we got earlier.
Bag of words model is a great technique, but it does have its shortcomings. So let's just go over the pitfalls of this model. One drawback is that if a new sentence contains new words, right, then the vocabulary size would increase. Thereby, the length of the vectors would also increase. Additionally, the vectors would also contain many zeros, thereby resulting in a sparse matrix, which is something we would really like to avoid. One more, one more drawback is that we are not retaining any information about the grammar of the sentence, nor the order in which the words are placed in the text. And sometimes that is a very vital information because let's consider an example. If the text says, "This is interesting," and there's another text which says, "Is this interesting?" Both actually convey different meanings. And if we don't consider the order of the words, then that vital information gets lost.
Term frequency and inverse document frequency. What is the importance of this technique? This technique provides weight to different terms. But you might be wondering, why do we need to add weight to different terms? Why can't we just treat all the terms equally, right? Well, that would be a bad idea because functional words such as stop words are dominant in the text in documents. So it it's a good practice if we follow this technique, and because through this technique we can know how relevant a particular word is to a document. Before we move into how this technique is implemented using an example, let's get familiarized with some common vocabularies. What is term frequency? Basically, term frequency tells us how often a word occurs in a single document. So this is our formula. Now let's move on to understanding what is inverse document frequency.
Inverse document frequency sheds some light on how rare or common a particular word is in the entire corpus of all the documents. So this is the equation or formula that is used to calculate the inverse document frequency score. So we check how many documents are present divided by number of documents in which that particular word is there. And we take the log value of that. And that will give us the inverse document frequency. If the value that we get is close to zero, it means it's a very common word. How to measure the relevancy of a word to a document? Well, all we have to do is multiply the two terms that we just learned, the term frequency into the inverse document frequency. Words such as the, is, on, and are quite common, not just in a document, but all the documents in the data corpus. That time the relevancy will be small because term frequency into the inverse of the document frequency value will give us a small value. But on the other hand, if the word if a particular word occurs quite often in one document, but if when we look into all the documents, that word doesn't occur that often, it means that it holds some special relevance in that particular document, right? So that time we can say that that word has high relevancy to a document. Cool. Now that we've got a high-level overview of the concept of TF-IDF, let's take an example and see how it all works.
Let's assume that we have a collection of 4 documents as follows. To find the TF-IDF score of each term in the document, we will first have to implement pre-processing. And once we have removed all the stop words and carried out all the pre-processing steps, we will have the following data. Our next step is to compute the term frequency. So here we count the number of times each of this term is occurring in that particular document. So the first document is sky blue. So blue occurs one time. There's no bright. All these words are marked as 0 because they do not occur in the first document. Whereas sky is marked as 1 because that occurs. In a similar manner, we go through each and every document and whichever terms are present, we count them as 1. Once that is done, we will normalize each of the rows, and hence you can see that the first row is divided by 2. So so it's normalized to 1, right? So this is divided by 2. All right. Once we have this table ready, we can move on to the next step. Next step is inverse document frequency computation. In this step, you will make a note of in which all documents or how many documents this word has occurred. So you can see that bright has occurred in 3 documents and can has occurred only 1 document. And once you have that list ready, you can compute IDF using the formula. So you can know that out of the 4 documents that we have, this particular word has occurred only in 1 document. Hence, its score is 0.602. Whereas the word sun has occurred in 3 out of the 4 documents. Hence, this value is more close to 0. So we can conclude that the word sun is more common compared to blue. Once we have TF and IDF scores ready, we can calculate the overall relevancy of each term in that document. So how do we do that? We multiply the TF and IDF scores. And you can see that once the multiplication is carried out, we can know the most important word in each document. So in our first case, blue word is the most relevant word in the document. In our second document, today plays a very important special role in the document. So in a similar manner, we can know which word is highly relevant to that particular document. Let us explore the Python working code with the same example. Alright, now let's see how TF-IDF technique can be implemented using Python. Our first step would be to import all the required libraries. Once that step is carried out, we need to import all the required data. So we will add the data in this format. So you can notice that we have used the similar documents and similar sentences that we earlier discussed. In this step, we will normalize the data, that is, we'll convert the text into lowercase and we will remove all the punctuations. So let's do that. You can notice here that we are capturing the total documents data. That is because while computing IDF, this will be necessary. All right. So this is our data corpus. You can see the list of documents that we'll be using for our example. Our next step would be to create a frequency matrix of the words for each document. So what we are trying to do here is we are carrying out all the pre-processing steps. That is, we are tokenizing the sentences into words or tokens, and then we are carrying out lemmatization. We are filtering out all the stop words, and then we are creating the frequency table. So in this result, you can see that each document is our key, and the value is the dictionary of the word frequency. So sky is occurring once and blue is also occurring once in this sentence. And yeah, similarly in all the sentences also, we've just made a note of how often that particular word occurs in each document. All right. So once we have this frequency matrix in place, we can start calculating the term frequency and then we can generate a matrix. To iterate, term frequency basically tells us how often a word occurs in a document. And how do we find this term frequency? Basically, if we need to divide the number of times a particular term occurs in a document divided by the total number of terms in that particular document after pre-processing. All right. Once we have this understanding in place, let's just execute these cells and understand the output. So you can see that sky is half and blue is also taking the value of half. This is because after pre-processing, this sentence gets reduced to sky blue, right? And sky is occurring once and blue is occurring once, and we normalize the row. So we will be dividing it by 2. So 1 by 2, which is half. Similarly, all the other values also follow the same logic. All right. Now that we have implemented all the above steps, we need to create a table for documents per word. What does that even mean? So this table holds the value of how many documents contains that particular term. So if that term is present in that particular document, then it gets incremented by 1. Okay, so now let's just see. So the, 2 documents have sky in them, and blue, there's only one document which has blue in it. And similarly, this is the count of how many documents has each of these terms in it. Our next step would be to compute the IDF matrix. So that is done by implementing the formula. So that's log of total documents. So in our case, it's 4 divided by the count of the documents that has that particular word. So let's just implement that. You might recall that there's only one document which has the term blue in it. So log of 4 by 1 is nothing but 0.602, right? In the similar manner, all the other values also match with the expected values. All right, now once we have the TF matrix and IDF matrix, we can easily calculate the TF-IDF score. So all we have to do is we have to multiply the TF matrix and IDF matrix and we will get the TF-IDF score. So that will tell us how relevant a particular word is. So let's just implement this cell. And let's execute this cell as well. So you can see in the first sentence, blue has the highest value. So we can conclude that blue is the most relevant word. So yeah, in the similar manner, we can know how relevant a particular word is to that document based on this score. So, what is our key takeaway from today's tutorial? We understood that there is a gap between the data sets which are available to train the chatbots and the input that the model takes in to perform its task. So we need to bridge this gap. And how do we do so? By performing NLP tasks like data pre-processing and data transformation so that we can convert this text into a more digestible form. That is, it gets converted into a numerical vector which can then be fed into the model so that it can perform the task that it has to. We covered a number of data processing methods such as tokenization, lemmatization, removal of stop words. Stop words are words which do not contribute to the deeper meaning of the phrase. And we understood the flow, how a text gets reduced to tokens and then it gets reduced to lemma. And finally, when we have a curated list of processed data, we then perform a number of encoding techniques so that it gets reduced to a numerical vector. We talked about two very common encoding techniques. That one was bag of words model and another was TFIDF technique. And then we explored all these concepts using Python and NLTK library.
Thanks everyone for staying till the end. If you have any questions, please do comment in the chat below and we will do our best to help you out. We also have a WhatsApp community group, so if you would be interested in joining, please see the link in the video description.